is now a pleasure to welcome on stage the next speaker, Professor Michael Klein. I was reading his bio and I was fascinated by all the different steps. He graduated at the University of Bristol in the UK, and then he did a postdoctoral researcher journey in 3 different countries: Italy, UK, US, started his independent career in Canada, and then moved back to the US and is now in Philadelphia. So looking forward to hear his journey. He's going to talk about understanding the properties of Teflon with machine learned potentials. Thank you very much.
Thank you for the introduction. Pleasure to be here again. Been here almost since the beginning. I probably gave the same talk 10 years ago, but there's a new twist to it at the end. So the twist here is, can we learn any more with the new tools that have arrived in the last decade or so? So my obligatory slide here is that it's an old problem, and by looking at it again, can we learn anything new? And I show my current inspiration, which is a photo taken of me preparing slides, which seems to be my #1 occupation these days. And I usually get help from Higgs boson. And the people that actually did the work are 2 very, very bright postdocs with me. One is a physicist, one is a chemist. And they are well trained in the art of producing machine-learned potentials. This is not an original activity in my group, as you'll find out. Others invented this toolbox, but it is proliferating rapidly with software tools that are available to everybody. So really here is the question we were trying to ask is, if we go back to an old problem, do these new tools teach us anything that we didn't understand before? So we focused on Teflon, which is a polymer analogous to polyethylene, except the hydrogen atoms are replaced by fluorine. And these are linear chains that crystallize like a bunch of pencils. They all line up in parallel. One of the surprises with this material when it was made is that they discovered that there were phase transitions, structural phase transitions, around room temperature. So when I gave this talk, quite famous polymer chemist Bert Meyer asked me, why do you do more research on covalently bonded polymers, which are destroying the world? And it's a very pertinent question. And even worse, why are you interested in forever chemicals, which are, once we make them, they're with us forever and ever, and they're not biodegradable? And so these are good questions. So in defense of this, I will say we're not proposing anybody make more Teflon, and so we're not adding to pollution. And it's unashamedly curiosity-driven. And I think if there is a message I want to give to young people, it's good to dream, and not every bit of science should have an obvious application. I think this is the privilege of being young. It's kind of sad now that when everybody writes a proposal, they have to speculate on how it might be useful. And I think if you track back in history, and I know Tony's worried about this as well, it's serendipity plays a huge role in these things. So this is one of those cases that was discovered by accident. The discoverer and his team were working at DuPont trying to make new refrigerants. And they used a gas in a cylinder, and they came in one morning and found that when they tried to turn on the tap from the cylinder of gas, nothing came out. So in the end, they opened it up, they tipped it upside down, and they found some white powder came down. And as it says here, they even had the courage to cut the cylinder in half, and they found they had made Teflon, the new substance. So this guy was honored quite quickly. In fact, after the Second World War, was honored in Philadelphia with the John Scott Medal given by the city of Philadelphia. I think it is the oldest prize in the US. Anyway, there may be older prizes in other countries. This historically is the older one. And I actually received this prize during the COVID, but I'm not talking about that work here. There's a very interesting thing here. The people that attended that ceremony were given Teflon-coated muffin tins, so I'm not so sure that that would be advisable anymore. Okay, well, so this was invented early on, and then we had the Second World War, so not a lot happened till after the war in science, at least nothing was published. And this article came out from DuPont Experimental Station, and they talk about the melting point, but they also describe a new way of making the stuff in the lab. And then some attempts to characterize it were made. There was a paper in Nature, the British chemical company Imperial ICI. By the way, ICI sponsored me as a postdoc. When I went back to University of Bristol, they still existed, and they were very generous in supporting me. Anyway, detailed studies showed that there was a 1% change in volume, and it's absolutely around room temperature. So you have to, if you're going to use it as a construction material, you should know that there's a phase transition depending on whether you're using this in the UK or in the US, the average, and where in the US you're using it. So let me go back and set the context for the 1950s. 1950s were really the beginning of helical polymers. So because these were potentially to be used in construction materials, there was a cautionary study here from the people in the National Bureau of Standards that said that actually this phase transition was two phase transitions. They did rather careful measurements and showed that it was a two-stage phenomenon. So not content with just doing the volume studies, they actually did heat capacity and showed indeed there were two phase transitions, and also identified the fact that if you cycle, you can make a glassy form of this material. That same period is more famous for the structure of nucleic acids, and I like to show this slide because it's important for the young people in the room to notice that science is actually done by young people and not people like me with gray hair. These people were kids when they did this, and this is a very important message. A paper that many of you might not appreciate, that after the structure of DNA came out, Peter Higgs wrote a paper and on infrared and Raman spectrum of helical polymers. I think this is largely unknown paper, and there's an interesting point here. He thanks Longit Higgins for discussion, and Longit Higgins was the professor of theoretical chemistry at Cambridge that replaced Leonard Jones, and genius character. I certainly heard him give lectures. He's sort of my generation. He was a generation before me, but he was a really inspirational figure who gave up theoretical chemistry to study how the brain works. So he left Cambridge and went to the University of Edinburgh and had a very successful career. He was obsessed with vision and memory, and I had a really wonderful lecture for him. And he was obsessed with the fact that if you hear 4 notes of Mozart, you immediately know it's Mozart. So our AI has a long way to go to catch up with the brain. You don't need to hear many notes of a famous. Okay, so Peter Higgs did this. and then 60 years later he got a Nobel Prize for the Higgs God particle. Okay, going back to Teflon, an X-ray structure was published showing how the structure changes through the phase transition, but it is still overridingly hexagonal. And so the basic packing of the chains hasn't changed as you go through the transition. And it says there's a reversible, and this is an important paper. So what is the structure? When they look in detail, what happens with polyethylene, where the fluorines are hydrogen, it's a zigzag chain. But the fluorines are sufficiently large that they bump into each other, and so they have to twist to avoid contact. The surprising finding is that the fluorines don't sit between the closest two fluorines. They actually are closer to one of the two than the other, and the bond angle opens up. So it's a non-trivial effect. It's not the minimizing the closest contacts, it's a collective behavior. And the chain, in this case, goes through 13 carbon atoms before it returns to the original position. And I'll say a little bit more about that in a minute. So about the same era, Rosalind Franklin was working on helical polymers. In fact, as we all know, the paper I showed before from Crick and Watson was inspired by her diffraction patterns, which they looked at. And in her paper, she actually acknowledges discussions with Watson and Crick. And this was a monumental work. It was the first structure of a virus. Of course, unfortunately, she didn't live long enough to be recognized for that, but the original paper's there in Nature, 1955. And again, helical, if you look here, and she shows in this picture how the helical pattern emerged. So this is 1955. Polymers had a significant event. I don't think, Andrew, it was celebrated, was it? The discovery of the folding crystallization. I know when I became an undergraduate, it was a big deal. I mean, everybody was talking about the fact that polyethylene does not crystallize with infinitely long chains that are parallel. In fact, they fold on themselves. And Andrew Keller was a very eminent figure. I never took lectures from him. He was a faculty member in physics at Bristol when I was there, but he never gave lectures to undergraduates. So then we go to 1958, and there was a Faraday discussion in 1958 that was absolutely magnificent. It was brought together by J.D. Bernal, who had become a crystallographer at this point, and he brought together people that were interested in macromolecules, large molecules, and was a dominant figure. He locally at that time, he was referred to as the sage, the guy that knew everything about everything, and the collection of papers that they brought together here. I don't know what happened to the mural that Picasso did in his lab. I think it was saved when the building was demolished, but you can find on the web a picture of it. So in this proceedings, there is a paper by F.C. Frank, which is the first serious theory of liquid crystals in this conference, was presented by him. And he did teach me solid-state physics, so a remarkable man who could sculpt air. We didn't have graphics in those days. When he was talking about Brillouin zones, he was sculpting the air to explain to you what the Brillouin zones look like. So I think I was one of the few kids that could actually follow him. So this is the paper I referred to by Andrew Keller. Is also, there was a communication, but there's an actual paper in this proceedings where he points out that the polyethylene they're making each of them is 6,000 angstroms long, but the diffraction pattern is telling you the repeat unit is only 100 angstrom. So how could that be? And then, and they know that the chains are parallel, so the conclusion is they must bend and fold back on themselves. So this is something that with modern computers and modern tools we can study, and we're not the first to do that. People like Don Franco and others have built models of this. And so there's something that we did in my group. Kyle Hall was the guy that did this particular study. And we studied the nascent formation of crystal nuclei of polyethylene out of a big melt. They were not 6,000 angstrom long. This blue one here is the one that you're seeing fold during the crystallization trajectory. And when did it stop? Could you put it back and start again? Go forward and see if it plays. No, I wanted that one, yeah, just see. Some reason the video's not playing. It played before. Well, I'm sorry. No, not working. Yeah, this is the usual PowerPoint problem. Here we go, okay. So this is a microsecond simulation, and how you get to this final configuration of this particular molecule. And so it's a competition between inter- and intramolecular interactions, and it likes to be close packed, but it turns out to be just as profitable to fold against another part of the chain. And the coloring here indicates that it's actually got 6 neighbors around it. And so that is what happens in that nucleus. Okay. So this is it's all been brutalized. Let's go on. Okay, so Rosalind Franklin also studied Teflon. So in this particular issue of the journal, unfortunately, by the time when the papers were submitted, she was alive, but by the time the conference happened, she died. And so the paper is published with the late Rosalind Franklin. And Aaron Klug, who was a groupie hanging out in her group, is the guy who wrote it up. And he was obsessed by, as he says here, by her crystallography of the viruses. And he went on and he got his Nobel Prize in 1982 for work that Rosalind Franklin originally published in 1955. And of course, he took it much further, but of course, he had years to do that. But in the same paper, Rosalind Franklin has a paper, again, the late Rosalind Franklin, where she studied Teflon. And the paper is about the disorder that occurs in the phase transitions. So to summarize, essentially there is a twist, a helical twist, which takes 13 fluorine atoms to repeat themselves. And then after the transition, it takes 15. So it's a very mild unwinding with the temperature change. And they identify something they call screw disorder. So you go through a transition where translational motion is occurring and rotational motion is occurring, but the helix itself is becoming undone very, very slightly. So it's a very subtle transition, and they identify what they call screw disorder. So again, this was a paper published after Rosalind Franklin had died. They didn't have computer graphics to try and explain that. They had a model built in the workshop of helical screw systems. which are built to the pitch of the actual Teflon molecule, so that the motion that occurs at the phase transition is this thing going up and down, but also the helical pitch changes, but only very slightly. So this was all known back in the 50s. So if you do the 3D model on the surface of a cylinder and you cut it and lay it open, you'll see that there are, I've labeled in red here, there are 6 helices, and that involves 13 carbon atoms, each of which have had 2 fluorines on them. So that's the phase transition. Now, this phase transition over the years has been studied by chemical physicists and all sorts of people to try and understand the spectroscopy. And in the 1960s, polymers were recognized as a big deal. So first of all, the helical polymer of DNA got its Nobel Prize, and Rosalind Franklin was not honored with that, as we know. But also other kinds of polymers was the following year. Ziegler-Natta for, I guess, commercial polymers. So other people at DuPont, where this was invented, went back and studied the spectroscopy. And very interestingly, there is a band here in this frequency range, 6, 7, 800 wave number region, which they identified as being due to a defect. So you have a natural helix. When the polymer forms, there can be defects where the helical twist reverses. So there is a reversal of the helix. And the idea is that this helix reversal can move up and down with very little cost of energy. But it stays as a defect, but it can move. So this was an important concept which was used to explain this. And this peak was studied as a function of temperature through the phase transition and so on. And people built models for that in the 60s. And the original suggestion from the guys at DuPont was substantiated by other workers in the subsequent years. And it became a focus of study to monitor the transition. I don't have time to really spend on that. Neutron people studied this, but again, I don't think that gave us any additional insights. And this is, again, example of what happens as a function of temperature with these 2 frequencies exchanging intensity below and above this transition. So this prompted people to not only do the measurements under normal conditions as a function of temperature, but people started to study these under pressure. And it was discovered that putting pressure on the Teflon stopped the helical twist and the chains became all trans. So that was a neat discovery that happened. And if we go forward, this has been the focus continually of more and more studies as you go through the years. And people speculated about other kinds of twist disorder that might be there. And in fact, I would say that there's no good low temperature study of what is the helical twist at very low temperatures to this day. And there even seems to be a problem with trying to ascertain what the density is, and that's why I highlight it here. You can find good papers that say the density is 2.2, and then another paper here says it's 2.3. That's a huge error in the density. And this is to do with the fact that samples can be amorphous and perhaps also have different helical pitch. So I think there are mysteries hidden there, and even more recent works. I'll go through those. Go even into the 90s. So here you get mobile helical twist coming out from a study. So up at the top right there, you'll see the phase diagram. So at ambient pressure, you see there's a very small sliver of this phase 4, and then you go into the high temperature phase, which is disordered, phase 1. It's the low temperature phase 2, where we don't have good, very low temperature data. And phase 3 is what happens when it becomes all trans at higher pressure. So there are lots of spectroscopic studies. And the focus of a lot of the work is on this helix reversal defect and twist disorder. So that is sort of summarized here. What are the various phases? And in the 30 years ago, people started to say, can we explain this on atomistic base models? And in fact, my group worked on this with 2 very brilliant postdocs when I was at University of Pennsylvania. And we elaborate on the kinds of defects that you can find and published papers on this and showed that these helical reversals could be mobile, and we thought that was pretty much the end of it. And then few more people went into this using other methods, and the huge difficulty in getting a quantitative model and force fields. Even though there were lots of publications, they were not definitive. And then the chemical physics people came into it, and it turned out that the determination of the quantum chemistry, if you want, of handling fluorine turns out to be very complicated. You can do it roughly, but when you want it quantitative, bearing in mind that there's a slight helical twist for these to avoid each other, to try and get that quantitatively is a real challenge. So Jorgensen wrote papers on this. And then the emphasis goes away from doing the full solid, and it shifts to looking just at single chains. And they don't do a very good job about the force around. The intermolecular force is kind of pushed aside, and the papers that come out in the last decade really focus on individual chains to try and build a quantitative model of the spectroscopy. So everything is a one-chain model. And they do a pretty good job of trying to use a careful modeling of a single chain to explain diffraction behavior. There's a succession of papers that every year or so come out with a new study. This particular paper was trying to push the idea that the helical defects are actually make a grain boundary, not just in the single chain, but in fact through the whole crystal. I don't find that credible. We don't see that in any of our models, but there are papers out there pushing that. Okay, I don't have time to go through these diffraction patterns in more detail. But a lot of emphasis is placed on whether there could be more than just 13-6, as it's called, 6 helical twists, or changing to 7 helical twists, whether there could be a hierarchy of these transitions as you go along the melting line or you cool. So let's move up to the more present days. People focus here on the high pressure behavior, but that in some sense is boring because they're all trans chains. So I don't think that teaches us too much. And then we go back to very recent papers, which are single chain models again. So people are not looking at the crystal field, if you want. And they claim to have a quantitative modeling of the helix defect there, that pair of modes that exist. So as these work. So this is a setup on a single chain model of what happens to the frequency of the defect. And again, it's kind of surprising to me that these turn out to be quantitative models. So we're getting to very recent. There's still papers coming out. These are top quantum chemists that are using much more sophisticated quantum chemistry to explain the 13.6 helix. And I think this is a great job, but it behoves us to try and model the solid, because the phase transition that occurs at room temperature is not a single chain transition. It is partly a helical unwinding, but it's a macroscopic change. So I'm just going to flick through these. There's still papers coming out. So is there anything left to do? And in the few minutes that I've got left, I'll just run through what we've been trying to do in my group. I think, as I said, the solid phases have not been studied in these single-chain models, even though they are very sophisticated. And the issue of the mobility, the dynamics of these helix reversals, are they really that mobile? I mean, if you do a single-chain model, is that adequate? And to go back and see whether the original paper by Rosalind Franklin and Aaron Klug, whether that's actually correct, that it's just simply twist disorder, and is it more complicated than that? So this really to set the scene. So in my group, I said there's two people working on this using high-level DFT and machine learning. And the advances that have happened in the density functional space have been driven by Michele Paranello, and my former colleague John Perdue, and Roberto Carr, and others. And I like to say, so when I prepared this slide, the number of citations to this paper was 228,000. But by the time I got here and looked on my phone, it's 233,000. Just in the time I've been here. So some people don't have one paper that will grow by 5,000 in your whole lifetime, but this is an extraordinary paper. And for the young people in the audience, there's a lesson from this paper. It's the title. The way people find work these days is by Googling keywords. And if you have a title that is 3 lines long, forget it. It'll never be discovered. So the genius of this is the title. So the generalized gradient approximation made simple. So if somebody wants to Google generalized gradient approximation, they will find this paper and get it more citations. So in the context of what we're doing now, these functionals have been systematically improved by John Perdue over the years. And when he joined the faculty with a brilliant postdoc and his wife, Adrian, this new, at the time, scan potential was used, and a bunch of us decided to test this immediately, and you've even got Umesh there, and we were staggered to find how good this was, how generally applicable it was, in fact, way beyond our initial expectation. And so we have used this as our way of generating structural information to fit machine learned models. I am not a contributor to this space. I want to say that others have done that. There are some incredible people active in this space, and I cannot pretend that I have contributed here. We shamelessly use what they have given us. But there is a message here that the pioneering paper for us in solid state was published in 2007, but it lay dormant. People didn't notice this for whatever reason. I don't know why, but it was there waiting for us. And it's only in the last less than a decade that this has exploded. So Roberto Carr picked up on it, and he had some brilliant collaborators. Linfeng Zhang, who was a graduate student that he shared with Wiener, and they essentially developed the toolbox for us to use this high-level density functional theory, and it's actually married to the quantum espresso code from the people in Trieste. And 2020 was when the massive application came out where they were able to use millions and millions of atoms. So this gave us the bridge from doing high-level calculations on relatively small systems that you could extrapolate with machine learning to literally millions. Actually, today it's billions, it's not millions. It's reached the scale of being able to do billions of particles. This is just in that short space of time. They're not the only ones to have done this. We've got Gabon in Cambridge has been very busy in this space, and also the people in Sandia Lab and Los Alamos also active, and now the people in Berlin very active in this space. In fact, I did a meeting in Rome at Temple University Rome campus in January 2020 because I wanted to learn about these things. So I invited all these people that were working in the field to come and spend a few days in Rome. So 2020, this whole machinery got prize from the supercomputing community, the Gordon Bell Prize, for this magnificent work that they'd done, Roberta Carr there. And also 2020, almost the last thing that Trump did when he left the White House for the first time was he signed the orders he likes to sign, and he essentially ordered the government to be active in the space of artificial intelligence. In fact, the driver for this is here. He actually had a science advisor there, and that prompted him to do that. So that had immediate effect where anybody that wanted research funding had to have machine learning in the title, or certainly had to allude to the fact that it would advance the field. And as we know, this has literally exploded. So I think I've used up my time pretty much. I haven't shown you what we've actually done, although we have 2 papers at the moment going through review process in Journal of Chemical Physics. They'll be out soon. We've tried all sorts of methods, and we found that you have to include van der Waals forces, not surprisingly. And the most primitive model of density functional theory, as I put here, it seems to be the one that is doing the best. It has a phase transition in the right temperature range. It seems to show the onset of a melting behavior roughly in the right place. More sophisticated models with much higher level van der Waals is hopeless. And we're trying to understand why that is, and it's to do with the modeling of the fluorine, which is turning out to be non-trivial. It's a very hard atom, and physically hard, has very little polarizability, and since the van der Waals is important, getting it right is proving to be very troublesome. So the sorts of things we've done, we've looked at phonons in all these things. I won't spend time on it. We can look at all the dynamics and so on. But to give a final point, to give some idea of the complexity of the infrared and Raman bands, they're far from easy. I mean, these bands contain many normal modes, and just to show some of the complexity, I'll go through some of them. I'm just skipping through the different modes that just this one band produce. I mean, there are many of them. At first blush, they all look the same, and that makes up this band. Anyway, so this is just initial statement. I thought I would have more to tell you, but it's turned out to be more difficult than I'd imagined, and so I'm going to end there. Thank you.